Imagine a place in the universe where the laws of physics break down, where time stands still and not even light can escape. These are the black holes, the gravitational giants where the information is lost. In this video, we'll be discussing the Hawking radiation, but before that, let's have a look about the contradictions between the general relativity and quantum mechanics in describing a black hole. At the universal scale, the theory of general relativity for Einstein states that the black hole is formed when a massive star collapses. It is a region in space where the gravitational pull is so strong where not even light can escape. It describes gravity as a bending space-time due to the mass and energy. On the other hand, quantum mechanics, which operates on the smallest scale, introduces concepts such as uncertainty and entanglement, breaking the classical physics rules, where vacuum isn't empty, but rather filled with quantum fluctuations everywhere and even next to the black hole's horizon. However, the main contradictions lie behind the event horizon of a black hole, as general relativity suggests that once an object crosses the horizon, it cannot return back or escape. In contrast, quantum mechanics states that quantum info is conserved and cannot be destroyed, and can help us to recreate the object from its particle components. This leads to the information paradox, which asks a question whether the information about matter that falls into a black hole is really lost forever or it still exists. By the way, there are some theories arise and state that the quantum info is encoded on the event horizon, where swallowing more objects makes a black hole grow enough in mass to conserve the quantum info. Yet they are so weak theories. In 1974, Stephen Hawking predicted that black holes aren't entirely black, where they emit a thermal radiation due to quantum effects, so-called Hawking radiation, which is a black body spectrum. This leads black holes to lose mass and evaporate gradually by emitting radiation according to energy mass equivalence equal mc squared. And now let's delve deeper into the topic. As I said previously, pairs of virtual subatomic particles, particle and antiparticle, are continuously being created and annihilating in the vacuum. However, just outside the event horizon, one particle falls into the black hole and thus having a negative energy according to the outside observer's perspective, which in turn reduces the mass of a black hole and leads to its gradual evaporation. On the other hand, the other particle having a positive energy escapes to the infinity, which we observe as a Hawking radiation, having an energy to be equal to the h bar, which is the reduced Planck constant multiplied by the speed of light cubed, divided by 8 pi multiplied by gravitational constant and mass of a black hole. And this leads to a new question. What is the relation between the temperature and the mass of a black hole? Due to the Hawking radiation, black holes have a Hawking temperature which is inversely proportional to the mass of a black hole, which is expressed by this equation. The temperature is equal to reduced Planck constant multiplied by the speed of light cubed divided by 8 pi Boltzmann constant, gravitational constant, and the mass of a black hole. This means that smaller black holes emit higher radiations or higher temperatures and soon evaporate faster compared to the larger ones. Thus, black holes and quantum information can both be erased.